It's my pleasure to welcome Andrew Childs from the University of Maryland. Andrew Childs is a professor in the Department of Computer Science and the Institute for Advanced Computer Studies, and he was a co-director of QUIX from 2014 to 2024, and is the director of the NSF Quantum Leap Challenge Institute for Robust Quantum Simulation. His research focuses on the theory of quantum information processing, especially quantum algorithms, and he has explored the computational power of quantum walks, provided an example of exponential speedup, demonstrated computational universality, and is constructing algorithms for problems including search and formula evaluation. He also focuses on developing fast quantum algorithms for simulating Hamiltonian dynamics. And this could actually be interesting for many of you focusing on the projects on quantum for climate, including energy and materials. Before coming to UMD, he was at Caltech and also at the University of Waterloo. And with his extensive experience, we are very excited to have you here, Andrew, for an overview on quantum algorithms.
Thanks very much. Yeah, thanks for the opportunity to kind of share my perspective on this topic. I guess you've heard, it sounds like quite a bit about quantum algorithms so far, but I'm going to try to give sort of a broad overview of kind of some of the main areas where we're sort of thinking about quantum algorithms and sort of the kind of also just the big picture about kind of the power of quantum computers. I'd like to start with that. So it's a big subject, and there's a limited amount of time. So at the end, I'll have some references that you can sort of go into for more details if you're interested in kind of more of a deep dive. This is going to be very much of a kind of a broad overview. Okay, so I would like to sort of first kind of introduce kind of the topic of quantum algorithms and kind of why we think quantum computers might have speed up and somehow what we have to do to look for cases where we can have significant quantum speedup. And then I want to sort of talk about, briefly about a bunch of different classes of problems where we think we can do something, that may be interesting with quantum computers. So these will be sections on quantum algorithms for algebraic problems, quantum walk algorithms, quantum algorithms for simulating quantum mechanics, quantum algorithms for high-dimensional linear algebra, and then I'll talk just kind of very briefly at the end about sort of optimization and machine learning, which are actually areas that maybe I'm personally less optimistic about, but we'll get there. Okay, so let me start with kind of an introduction to sort of how I see the challenge of quantum algorithms and what it is we're trying to do and sort of where we need to look. So there's this idea that somehow if we can build quantum computers, we can use them to solve some problems a lot faster than we could with ordinary classical computers. But where does that come from? Like why would we expect quantum computers to be more powerful or able to solve some problems faster? And, this is a kind of a probably a deep and complicated question, but if I had to point to one thing, it's really kind of the possibility in a quantum computation of having interference between different paths of the computation. And there's this kind of wave-like, kind of nature of the computation. And our goal is to sort of arrange our quantum computation so that the paths that lead to the solution interfere constructively and the paths that would lead to non-solutions interfere destructively. And so, when you have your final quantum state, it sort of is supported on the solutions. And, of course, wave phenomena are not somehow uniquely quantum mechanical. Like we also have classical waves, but the thing that's special about these wave phenomena in quantum mechanics, and specifically in a quantum computational context, is that with a quantum computer, you can give a very efficient representation of very high dimensional interference phenomena. So if you arrange things in the right way, you can maybe have these kinds of interference phenomena lead to a solution in a way that you wouldn't be able to efficiently realize that solution with classical waves. Okay, so that's kind of the underlying picture that I have in mind. But now the question is really like, what are the problems that where you can hope to get speed up from this? And I think it's really kind of important to realize that, quantum computing is not somehow a magic bullet that just will solve any problem a lot faster. And in particular, quantum computing is not the same thing as just like exponential parallelism, where somehow you can try and superposition all these possibilities and somehow magically pick out, the thing that corresponds to a solution. So, you can think about this sort of like needle in a haystack problem, and I guess you have heard about Grover's algorithm, which is basically a quantum algorithm for solving this problem, somehow trying to find a needle in a stack of n pieces of hay, and somehow what's achieved by this Grover algorithm, which is this quadratic speedup over a classical search, this ability to find this one thing out of n in only square root of n steps instead of the n that it would take classically, this is really the best that you can hope to do in some kind of black box model of the computation, right? So there's this lower bound of Bennett, Bernstein, Broussard, and Vazirani that shows that in a certain model that we call quantum query complexity, actually you need to query the input square root of n times with a quantum computer to find the thing that you're looking for. This is basically a consequence of the linearity of quantum mechanics. And so, what this kind of tells us is that if we want to get significant speed up, for this problem, but I think this is also true more generally, we need to have some structure that we can exploit, right? We can't just sort of, view the problem as this kind of like completely unstructured thing and just sort of rely on the magic of quantum mechanics to find the thing that we're looking for. We can get some advantage from doing that kind of thing, this kind of quadratic speed up, this kind of quadratic advantage that you've seen from Grover's algorithm, but that's kind of the best you can do unless you sort of have more going on. So to me, kind of the key question about quantum algorithms is to understand, what are the kinds of problems that have some structure for which we'll be able to do this kind of high dimensional interference with a quantum computation in a way that gives us a big savings over what we could do classically. And this is this is not an easy question, and we definitely don't have anywhere near a complete understanding of what this sort of structure looks like generally. Nor do we have that many examples of places where we can find this kind of structure. So this is kind of the thing to do in quantum algorithms, to find more examples of problems like this and to try to get a better kind of overall picture of what are the things that allow for significant quantum speedup. And at least in my view, if you want to sort of approach a problem with a quantum computer, you really should have a reason to think that it has that right kind of structure that's going to allow for things to be a lot faster, because it's definitely not a very generic thing. So I want to talk about another example that kind of relates to maybe some quantum algorithms that you've seen before that I think maybe makes this point even a little bit more vividly. And this has to do with Simon's problem and a related problem called the collision problem. So Simon's problem, I guess you've seen before. So let me just briefly recap what the problem is, right? So you've got this black box function that maps, let's say, strings of n bits to some range. It doesn't matter so much what this set is, but you have this promise that the values of this function are somehow very structured. They're structured so that if you look at what happens when you query the function on inputs, different inputs x, those inputs can be broken up into pairs. And some particular input x is going to be paired with another string, which is x XORed with some special string x bitwise, right? So there's like this hidden string s. It's also an n-bit string. And the way you can find two inputs that evaluate to the same thing under this function is you take the one you started from and you XOR it with s, right? So like the all zero string is paired with the string s. The string that's all zeros followed by a 1 is paired with the string that just flips the last bit of s, etc. Right? In general, x is paired in this special way with x XORed with s. Right, so this kind of hidden string is imposing a lot of structure on how this function, looks. And our goal in this problem is to find s. And I guess I think you've seen the quantum algorithm for this problem before, and maybe you've also heard about the classical hardness for this problem. So one way of trying to solve this problem classically is just to query the function at a bunch of randomly chosen places until you find a collision, right? If you find distinct inputs x and y, such that f evaluates to the same thing on x and y, right? F of x equals f of y, then you can XOR together x and y, and that will tell you s. And by this thing called the birthday problem, this kind of standard problem in probability theory, you can show that you need about the square root of the total number of possible strings, in other words, the square root of 2 to the n, random queries before you expect to find such a collision. And this is basically an optimal strategy for this problem. So this is really like the best you can do. But quantum mechanically, you've seen that there's a one query algorithm that will basically learn one bit of information about s, right? It basically gives you kind of one linear equation that tells you something about s. And if you query a linear number of times, then you can determine what the string s is with good probability. So basically, the quantum query complexity of this problem is basically linear, as compared with this exponential query complexity classically, right? So this is like an exponential savings of the quantum algorithm over the classical one. So I want to contrast this example that you've seen before with another example that maybe you haven't seen before, which is what's called the collision problem. So in the collision problem, you're also given such a function, and now you've got some promise. Let's say it's either a 1-to-1 function or a 2-to-1 function, right? And just to make things simple, like let's say your goal is just to determine which of these things is the case. Right. So if it's a 2-to-1 function, that means it's a function that looks like what we have in Simon's problem, right? That if you look at the kind of the possible inputs to the function, you can pair them up into pairs of inputs that evaluate to the same thing. So these black dots represent inputs, and these two inputs evaluate to the same thing. These two inputs evaluate to the same thing, etc. And then the other possibility is just that it's a 1-to-1 function, meaning like everywhere you evaluate it, you get a different output. Right? And now you want to determine which of these things is the case. And so you can show that quantum mechanically, you can solve this problem in n to the 1/3 queries. So n is this exponentially large thing. It's the number of possible bit strings. You can show using Grover's algorithm. That's a nice exercise to show how to do this. Maybe we don't have to go through the details, but you can show that with n to the 1/3 queries, you can solve this problem. But that's still exponentially many queries. And in fact, you can show that this is basically optimal. This is actually the best you can do, even with a quantum algorithm, right? So for this problem, there's no exponential quantum speedup. There's some polynomial quantum speedup that you can show that the best you can do classically is basically this birthday problem thing. It's like the square root of n. So there's a little bit of quantum speedup, but it's not exponential quantum speedup. Okay, so what's going on here? So we also had this 2-to-1 kind of structure in Simon's problem, but in Simon's problem, there was much more structure, right? Because these things were paired up in a way that had to do with kind of the bit representations of these values, right? X was paired with X XORed with S, right? So that there was like a lot more structure in the Simon's problem that the quantum algorithm is taking advantage of in order to be able to do things much faster, right? If you had this collision problem and you were promised that in the 2-to-1 case, the function had the structure of the Simon problem, then you could actually solve this problem very efficiently in time, poly log capital N, right? Polynomial in little n. So there's what's going on is that there's like a lot more structure, and with this additional structure, we can get significant quantum speedup. And so this is basically what we sort of want to understand in general, right? So the collision problem doesn't have enough structure to give us a fast quantum algorithm. But in Simon's problem, we have some particular structure that we can latch onto that allows us to, with this kind of Hadamard transform on some particular kinds of quantum states, solve the problem a lot faster. And this gives us exponential speedup. So, what we want to understand in general is like, what are the problems that have fast quantum algorithms, but not fast classical algorithms? And kind of more broadly, what are the kinds of structures? So for example, the structure that's here in Simon's problem is a structure that kind of enables significant quantum speedup. But what are the other structures that enable significant quantum speedup? And there are some others that are known, but there's definitely not a very good kind of overall understanding of this question. And of course, it's not. I don't want to completely discount the possibility of having something interesting happen with less than exponential quantum speedup. I think it's also interesting to think about when we can get polynomial quantum speedup, and when that's the case, how much polynomial speedup is possible. So that's also a thing that's definitely worth studying. But we're definitely going to get the most bang for our buck when we try to build a quantum computer if we can really get exponential quantum speedup. Okay, great. All right, so now what I would like to do is sort of talk about a bunch of different, kinds of quantum algorithms, some sort of like families of quantum algorithms, and just talk a little bit about what's known, and kind of where things might be headed in the future. Okay, so let's start out by talking about algebraic problems, which many of these quantum algorithms for algebraic problems have to do with kind of identifying hidden symmetries, right? So the Simon problem, can be thought of as an instance of this more general family of problems that have to do with identifying some sort of hidden symmetry. Shor's algorithm for discrete log and also the factoring algorithm can be seen as doing something very similar to this. And there's a kind of a general class of problems that has been studied called the hidden subgroup problem that kind of formalizes this idea of identifying hidden symmetries. So in the hidden subgroup problem, you're given some group, So you know what this group is, and then you're given the ability to query some black box function that maps elements of the group to some range, and you've got a promise about the structure of the function. So this is a promise that, maybe in some cases could be helpful for getting significant quantum speedup. The promise is that the function basically like respects the symmetry of this group in some sense, specifically that it's constant on cosets of some subgroup of the group. So there's some unknown subgroup H of G, and it's distinct on different cosets, right? So you can sort of cast the Simon problem in this sense for some particular group, but you can do this much more generally for other groups. And so you have this picture where you've got this function that takes one value on, let's say, the elements of the subgroup, and then different values, different constant values on different cosets of that subgroup. And then your goal is to figure out basically what the subgroup is. And there's an approach to this problem, which is the approach that's used in the algorithm for Simon's problem that you've seen, which is sometimes called the standard method. So the idea of this approach is that you take a uniform superposition over the elements of the group, and then you query the function in superposition on all of those elements, and you basically like discard the information about which function value you have. That basically is going to project you onto a uniform superposition over the elements in one of these cosets. And you're not going to know which coset you get because you're just going to get some function value. These function values don't really mean anything to you, but you're going to get one of these coset states. So this, pictorially, this is like a uniform superposition over the elements within one of these cosets. Okay, so this problem can be considered for all kinds of groups. And if we think about the special case where the group is abelian, where this group G is abelian, then there are lots of applications of quantum algorithms that are known in that setting. So you can think about the discrete log algorithm as an instance of that kind of a problem. You can think about factoring in this sense, but now here the group really should be kind of formally infinite. There's maybe some question about how you sort of like handle that with a digital computer, but you can. And then there's a bunch of other sort of like number theoretic kinds of problems that can be cast in terms of problems that have to do with finding hidden subgroups of abelian groups, like, for example, problems relating to counting points on certain kinds of algebraic curves, or various kinds of problems in number theory, some of which relate to cryptography. So there's a bunch of kinds of problems that we can sort of approach in this way. Another thing that can be put in this framework is kind of the case where it comes from the case where the group is non-abelian, so where the elements of the group do not commute. And a lot less is known about this case. So in this case, you can show that polynomially many queries to the black box suffice. So these coset states can be used in principle to find what the hidden subgroup is with only polynomially many queries to the black box. But whether there's an efficient quantum algorithm that can sort of process those states with only polynomial running time to determine what the hidden subgroup is unclear in general. So there are some special cases where it's known how to do that. But on the other hand, there are some hidden subgroup problems that, if we could solve them, would have really, really interesting applications, but for which we don't know how to solve them efficiently. And probably the kind of most exciting of these is, has to do with what's called the dihedral group, for which, if we had a solution of the hidden subgroup problem that kind of follows the framework that I sketched, we could actually give quantum algorithms for lattice problems, which are the leading candidates for quantum secure cryptosystems, right? So the kind of fact that Shor's algorithm breaks RSA and Diffie-Hellman and other kinds of public key cryptography has led to this interest in finding cryptosystems that would resist quantum attacks. The leading candidates are based on these lattice problems, which there would be attacks on if we had quantum algorithms for this dihedral hidden subgroup problem, but no such quantum algorithms are known. And in fact, no efficient quantum algorithms for these problems are currently known. So, that's one of the reasons people have been interested in this hidden subgroup problem. I would say progress in this direction has kind of stalled in recent years. There are some kind of hardness results about the kinds of processing you would have to do on these states to recover the hidden subgroup. These results are kind of far from ruling out the possibility of an efficient quantum algorithm, but we also don't have a lot of great ideas for how to move forward in terms of finding better quantum algorithms. So this is I think it would be a nice area to make some progress on, but not one where there has been much progress recently. Okay, so that's just a very quick overview of this kind of area, but in light of the time, let me maybe move on and tell you about some kind of other areas in quantum algorithms. And I'd like to talk a little bit next about this idea of a quantum walk on a graph. The idea of a quantum walk has to do with trying to come up with a quantum mechanical analog of a random walk or a Markov process. Random walks or Markov processes are really useful tools for classical algorithms. And so it's natural to imagine that if we could come up with quantum analogs of them, we could do interesting things with quantum computers. And so that's the reason that people have spent a lot of time studying what quantum walks might be useful for in a quantum context. So the kind of idea of defining this notion of a quantum walk on a graph is basically to think about replacing the probabilities that characterize the dynamics of a random process, like a Markov chain, by quantum amplitudes. And so you can get an analogous but totally different process. And since now you can have interference phenomena occurring in the quantum walk, you can have radically different behavior. So for example, here's a picture of what the classical random walk distribution of a classical random walk on a line might look like. If you start at the origin and you sort of randomly decide whether to move left or right, you get this kind of Gaussian sort of spreading of the probability. And quantum mechanically, you have some interference that takes place that allows you to move much faster, further away from where you started, and you have this more complicated looking distribution. And so the kind of hope in this area has been to try to use these quantum mechanical processes on graphs to find faster quantum algorithms. So let me maybe mention a few of the things that are known about what these quantum algorithms can do. To do that, let me first formulate a little bit more precisely what I mean by the quantum walk. And there's actually different ways that you can define a quantum walk. Two natural ways involve doing it with a process that sort of evolves continuously in time, or one that evolves with discrete steps in time. And it's actually, in some ways, a little bit simpler to think about the one where the walk evolves continuously in time. So let me briefly introduce that. So imagine that we have a graph. So we have vertices, and then we have edges that join the vertices that describe sort of things that are next to each other in the graph. And we can characterize that graph by a matrix called the adjacency matrix, where we have entries that are 0 and 1, where the ones correspond to vertices that are adjacent. So for example, vertices 1 and 2 are adjacent, and that's why there's a 1 in the 1, 2 entry of this matrix. We can also define another related matrix called the Laplacian of the graph, which is basically the matrix where we have, it's like minus this matrix. So we have minus ones in the off-diagonal entries corresponding to the edges of the graph. And then on the diagonal, we put the degree of the vertex, like the number of edges coming out, right? So like vertex 1 has 2 edges coming out, so we put a 2 there. So this is a kind of you can think about this as kind of like a discrete approximation of kind of the second derivative operator on the graph. And now if you want to define a random walk, a continuous time random walk on the graph, you can do it by saying, okay, we've got a vector of probabilities. PV of t is the probability of being at vertex v at time t. And then consider this differential equation. The kind of derivative of p is the Laplacian acting on p. So this is going to describe some kind of diffusion of the probabilities on the graph. But quantum mechanically, imagine that instead of sort of trying to capture these probabilities, you want to understand how these amplitudes evolve. So you've got an amplitude AV of t to be at vertex v at time t. And if you just put an I into this equation, right? So this equation is just the same thing, except we put an I in front of the derivative. Then this is going to describe unitary dynamics on the graph, where now you're going to have interference, as you do in quantum mechanical processes. And so it's going to be in some ways analogous to this classical process, like the amplitudes will evolve locally on the graph. They sort of move around locally. But now we have the possibility of interference, and the dynamics can be very different. Okay, and yeah, there are maybe different ways of defining this that all kind of make sense quantum mechanically, but maybe let's not worry about it. Okay, so one example of kind of a significant quantum speedup that was discovered using this idea of a quantum walk on a graph, came from this continuous time walk model, and it works as follows. So imagine that you construct a graph by taking two binary trees, and then you join the leaves of the binary tree on the left with the leaves of the binary tree on the right by sort of a random cycle that alternates between the left side and the right side. So you go back and forth until every vertex here has two neighbors to the right, and every vertex here has two neighbors to the left, right? So then when you do that, you have this kind of mess where almost every vertex in this graph has three neighbors, except this one that I labeled in has two, and the one that's labeled out has two. And now our goal is to sort of like think about this as sort of like a maze where we started in and we want to find our way to out. And you can kind of formalize this by a black box model where the vertices have labels, and you have a function you can call that if you supply it with a label, it will give you the labels of the adjacent vertices, right? So that's like a way you can sort of explore this graph or walk around in this maze, by sort of starting at some vertex whose name you know, and then querying the black box to find your way to other places in the graph. Right? So suppose you're given the label of this in vertex, and your goal is to find the label of the out vertex. Well, quantum mechanically, what you can do is you can run a quantum walk, this kind of continuous time quantum walk that I introduced on the previous slide, starting from the in vertex. And what you will find is that it stays within a simple invariant subspace of the full vertex, the full Hilbert space that this quantum process explores. It stays within these uniform superpositions over vertices in a given column of this graph at a certain distance from the in vertex. And because of this, you can show, I mean, there's a calculation you have to do, but you can show that the walk will reach this out vertex in a small amount of time, like in an amount of time that grows something like the height of this tree, whereas the number of vertices in the graph is exponentially large as a function of that parameter. So what that tells us is that this quantum walk will actually basically reach this out vertex, and you can use it to solve this computational problem of finding the label of the out vertex. But you can also prove that a classical process, a classical random walk, but also actually any classical process that any classical algorithm you can try to run, will not be able to, in polynomial time, find the label of the out vertex. So this is an example of a quantum walk getting an exponential speed up over what can be done by a classical algorithm for a kind of a toy problem. You can think about this as kind of like an analog of Simon's problem, but for quantum walks. So this is kind of encouraging because it says that this quantum walk idea can be really computationally powerful. There are also other things that we can do with quantum walks, and there's also other kinds of quantum walks that we can define. And for some purposes, it's useful to have a notion of a quantum walk that takes discrete steps in time rather than being defined as a continuous time process. This sort of, for technical reasons, is a little bit harder to define. Actually, maybe I can just sort of explain why this is harder to define. So like, imagine you wanted to define a discrete time process that moved you in superposition just on a path. So then you would like to move from, let's say, the vertex X to a superposition of the two adjoining vertices. This would be a natural way to sort of write that down. But this is actually not a unitary process. Like, you can show that if you would do this, it would evolve orthogonal states to non-orthogonal states. So that's actually not a valid quantum process. Like, it's not a thing you could do on your quantum computer. And it turns out that there's kind of a way around this, which has to do with this notion of introducing what are sometimes called coins, basically another register that remembers a little bit of information about where the walk was in the past, kind of remembers the previous position. And this remembering will sort of reduce the potential for interference a bit, but only a bit. And so, that won't be a major problem for getting kind of significant interference that can lead to computational speed up with these processes. So there's a kind of a process that you can, or a procedure you can go through to define such a discrete time quantum walk, which is kind of outlined here, kind of starting from any classical Markov chain. Maybe in the interest of time, I won't try to kind of explain all of the details, but maybe you can just trust me that it's possible to define a unitary operator kind of corresponding to an underlying Markov chain that gives you some kind of quantum analog of that process. And these discrete time quantum walks are also useful for getting some quantum speedups. One kind of framework where they're useful is this idea of quantum walk search, which is a way of solving some kind of search problems where the way you explore the different states that you're searching over, it comes from some given graph. So let me define this setup. So imagine you're given some graph. So you've got vertices and edges. Some subset of the vertices are considered marked, and your goal is to find one of these marked vertices. Or you could think about the decision problem of figuring out whether there are any marked vertices. So that's this question of just determining whether the marked set is empty. And now there's a natural way of doing this, which is basically just to walk around on the graph at random, right? So take some random walk on the graph until you happen to reach a marked vertex. Start from maybe a uniformly random, vertex of the graph, and then walk around at random until you find a marked vertex. And if you follow that strategy, then the time that it will take to hit a marked vertex basically goes like 1 over delta times epsilon, where delta is a parameter that basically captures how fast you move around the graph, sort of how rapidly you get lost if you just start walking around at random. Formally, it's this thing called the spectral gap of the walk. And epsilon is just a fraction of marked vertices. So like the more vertices are marked, the easier it's going to be the easier it will be to tell the case where some vertex is marked from the case where no vertex is marked. Lots of marked vertices makes it easier to find one. So this is the time that it will take to hit a marked vertex. And you can show that quantum mechanically, if you consider this discrete time quantum walk that was introduced on the previous slide, you can construct a process that can be used to find a marked vertex or tell whether there is a marked vertex quadratically faster. And sort of some of the details about how this is done are mentioned here. You strictly speaking, you define sort of this discrete time quantum walk corresponding to kind of a slightly changed process where what you do is you stay at a marked vertex if you reach one. This is this notion of an absorbing walk. And then what we're going to do is not just walk around and see where we go, but we're actually going to run a process called quantum phase estimation to get some information about what the walk is doing. But if you sort of like sort out these technical details, basically the bottom line is that we can sort of like determine whether there's a marked vertex in the graph kind of quadratically faster than we would be able to find one by this classical process that walks around until it hits one. And this idea of quantum walk search is sort of a primitive that you can think of as generalizing the Grover search algorithm. And it can be applied in some cases where you can't kind of directly use Grover search to get quantum speedup. You can sort of think about the unstructured search problem as coming from the case where you have like the complete graph and you've just got, let's say if you've got, you could have only one out of the n items could be marked. So this fraction of marked vertices could be 1 over n. The spectral gap of this graph is really big. It's basically constant. And so if you plug into these formulas that I gave on the previous slide, you find this kind of quadratic speedup that you get from Grover's algorithm. But there are other problems for which you can get quantum speedup from this framework that Grover's algorithm sort of wouldn't give you. And the most famous of these, and the one that kind of originally motivated this framework, is something called the element distinctness problem, which is basically a problem having to do with finding some kind of collisions. You want to know for this function, is there a distinct pair of items x and y for which f of x equals f of y? And yeah, maybe in light of the time, I won't try to kind of go through the details about how this works in this framework, but I'll just say that, classically, basically, there's sort of nothing you can do better for this problem than just to query the function on all the possible inputs. But quantumly, there's a way of walking on a certain graph called the Hamming graph, for which you can get some speed up. And you can get, what you can show is that you can get, you can find such a collision, or rather you can tell whether there is such a collision with a complexity that goes like n to the 2/3. So this is an example of a problem with polynomial quantum speedup, not exponential quantum speedup, but one for which there's some structure that you can use to get some quantum speedup. And more generally, you can apply this idea of quantum walk search to get speedups for other kinds of problems. Okay, so that's a kind of very quick introduction to some of the things that you can do with quantum walk algorithms. In light of the time, I think I'm going to move on, and I'm going to talk a little bit about Hamiltonian simulation. Okay, so Hamiltonian simulation is really one of the major potential applications of quantum computers. I think it's probably the one that's sort of likely to bear fruit the soonest, and I don't know, maybe to bear the tastiest fruit, because it's it's a problem that probably, unlike, let's say, factoring, we really want to solve. We really want to understand the behavior of quantum mechanical systems, and it's a problem that really is hard as well for classical computers. So maybe you've seen before this kind of quote from Feynman, where he sort of identified this problem of simulating quantum mechanics as a really natural thing to do with a quantum mechanical computer. This was kind of the problem that led him and others to sort of first think about this idea of a quantum computer. And so this problem, as we sort of now understand it, is basically the following. So we've got a description of a quantum mechanical system specified in terms of an operator called its Hamiltonian. That's like a Hermitian operator that basically tells you about the energy levels of the system and will define the dynamics of the system, how it will evolve in time. And then you're given an amount of time you would like to evolve for. You're also given an initial state of the system in the memory of your quantum computer, and your goal is to figure out what the dynamics of that system would do. So what the quantum state would be, at this final time t. And it's maybe enough to do that approximately up to some error tolerance epsilon. And this is, the goal here, I should say, is not to, give a kind of a complete description of what this state is, but rather to produce a copy of this state in the memory of your quantum computer. And then that's something that you could use, you could perform measurements on to learn things about the state of the quantum system. But I'm going to sort of not think about that part of the problem and just think about the problem of simulating the dynamics in this sense of like producing the quantum state. Okay, so, this problem, as I'm describing it, is an inherently quantum mechanical problem. We can't hope to, even represent general quantum states efficiently on a classical computer. And, the quantum computer is somehow not giving you that complete description. It's just giving you this quantum mechanical representation. But there is a sense in which this is a problem that, a quantum computer can solve and a classical computer, cannot, at least if there's anything that a quantum computer can do that's, not simulatable by a classical computer. So we say that this is an example of what's called a B2P complete problem, which basically means that it characterizes the difficulty of what quantum computers can do, right? So like any problem that can be solved efficiently by a quantum computer, for example, factoring, could be cast as an instance of this Hamiltonian simulation problem. And this is a problem that can be solved efficiently by quantum computers. Okay, so this is, I think, quite an important area of quantum algorithms. And there's kind of two reasons maybe to care about it. One is the kind of reason that maybe you want to think about physics, right? You want to understand what happens with some molecules where quantum mechanical effects are important, or you want to understand about some materials, or you want to study, nuclear or particle physics. Basically, any kind of theory of physics where quantum mechanics plays a role, you can imagine trying to do quantum simulations to get a handle on what's going on. But you can also imagine using quantum simulation to implement algorithms that are stated in terms of Hamiltonian dynamics. So for example, these continuous time quantum walk algorithms that I mentioned before are examples of algorithms that are defined by some Hamiltonian dynamics. And if you want to run those algorithms on a universal quantum computer, you need an algorithm for simulating Hamiltonian dynamics. To do that, even if the underlying problem you were trying to solve kind of had nothing to do with, simulating physics. And there are other examples of problems, not all of which I'll have time to talk about, but there's some other examples of problems that have quantum algorithms that have been discovered from this kind of picture of thinking about, kind of Hamiltonian dynamics. So this is another reason to maybe try to have fast algorithms for Hamiltonian simulation. Okay, let me give a kind of a very quick introduction to some of the main algorithmic ideas that are out there for simulating Hamiltonian dynamics. And the most obvious of these has to do with what are called product formulas. So, if we've got some Hamiltonian we would like to simulate, well, it's a Hermitian operator. And in general, you can write such things as a sum of terms that are in some sense simpler. So if you have a spin model, you might have your Hamiltonian might be written as a sum of terms that act kind of locally on small numbers of the spins. But more generally, you can have other situations where you've got some big complicated Hamiltonian and you have some way of decomposing it into simpler pieces that individually are easy to simulate, for which the dynamic corresponding to one of these individual HLs would be something that there would be an easy quantum circuit for. And what product formulas do is they allow you to express the dynamics according to the Hamiltonian H as a product of evolutions according to the individual terms HL. So if we think about the case where we just have a sum of two terms, so like H is equal to A plus B, then a way of sort of expressing this matrix exponential, this e to the minus I ht is the unitary operator that describes the dynamics of the quantum system with the Hamiltonian H. Now, this is, of course, not in general the same thing as e to the minus iat times e to the minus ibt if A and B don't commute. And for an interesting situation, these terms will not commute. But it is the case that if you kind of evolve a little bit according to B, and then a little bit according to A, and then a little bit according to B, and then a little bit according to A, and you go back and forth, in the limit that you go back and forth kind of arbitrarily fast for arbitrarily short evolution times, you can get the correct evolution according to the full Hamiltonian. And now what you can do to get an algorithm for this is to think about truncating this expression at a finite value of r. Right? So if I take this thing and I fix some particular value of r, then I'm not going to get exactly this, but I'm going to get that up to some error term. And you can kind of quantify how big that error term is. And then you can understand how big r has to be so you get an accurate simulation of the dynamics. And so you can do this with kind of this expression that's written here, but you can also get even better approximations by using sort of higher order approximations. So, so this expression that's written here is like something that's accurate to one more order than this expression, right? So this is like a first order approximation. This is a second order approximation. And in fact, you can even systematically construct approximations to arbitrarily high orders. This was actually done kind of even before the kind of model of quantum computers was pinned down as part of kind of classical numerical methods. It was developed by somebody named Suzuki in the early 90s. And this gives you quantum algorithms for simulating Hamiltonian dynamics that have cost that scales like this as a function of the evolution time t and as a function of the error epsilon that you allow. You know, there are other algorithms that have been discovered that use completely different ideas. So rather than sort of decomposing the evolution into products of these kind of elementary exponentials corresponding to simple terms in the Hamiltonian, they do completely different things that achieve kind of better asymptotic performance as a function of the parameters we care about. So as a function of the evolution time t, and also as a function of the allowed error epsilon. And so, you know, there's an algorithm that has complexity that scales actually linearly in t, which you can show actually is the best you can hope for. So this kind of no fast forwarding theorem says that that's the best you can hope for. You can actually, there's a method that, you know, I won't get into in detail, but there's a method that actually achieves that exactly. And there's also a method that sort of gets the optimal dependence on the allowed error epsilon, which uses a completely different approach that basically, in some sense, directly implements the Taylor series of this evolution operator. So that's the sort of method that's alluded to here, using this notion of, you know, what are called linear combinations of unitaries. So there are a bunch of these algorithms that have been developed to try to get better asymptotic performance as a function of certain parameters. You know, a sort of like even more sophisticated method that was developed kind of following these methods is this thing called quantum signal processing. And you know, this actually gets not just sort of like, you know, really good dependence on the evolution time t and the allowed error epsilon, but actually the sort of optimal trade-off between those two things. So it's a somewhat more complicated algorithm in some respects, but gets this kind of better asymptotic performance. And a kind of another thing that has been studied is if you have Hamiltonians that have geometrically local terms, so spatially local interactions, then sort of you can take advantage of the locality of the Hamiltonian to give algorithms whose complexity scales more efficiently as a function of the system size. So, you know, the details of all of these algorithms, you know, it would take a lot of time to sort of really get into. But I guess the main sort of message I want to convey is that there are a bunch of algorithms that have been developed, these so-called post-Trotter algorithms, that achieve better asymptotic performance, you know, in various respects by doing different sorts of things. And it's a little bit unclear, you know, whether these algorithms will be, or in what context these algorithms would be really good to use. But I also want to mention that some kind of improvements to the analysis of these product formulas has actually, you know, suggested that those are really, in a sort of a practical context, you know, often really the best thing to do. They're really, in some sense, the simplest kind of algorithm to sort of say what it is and to and also to implement. They actually, you know, can perform much better than the kind of most straightforward analysis would suggest. And you know, this kind of analysis comes from some kind of fancy integral representations of the error. This is maybe like the simplest instance of such a formula. These formulas basically allow you to sort of take advantage of commutation between different terms of the Hamiltonian that can, you know, give you, sort of tighter bounds on the error and therefore more efficient algorithms that don't have to split the evolution into time segments that are as short and therefore will use fewer gates overall to give a simulation to a given desired accuracy. You know, this method can even show that, for example, these algorithms for Hamiltonians with geometrically local interactions, you can do almost as well with simulations using product formulas as you can using these more sophisticated algorithms. There are also now a bunch of algorithms that have been found that sort of use information about the initial quantum state to sort of do even better. So I guess the main message I want to convey here is that, what sort of happened, or at least from my perspective, in this kind of general area of algorithms for simulating Hamiltonian dynamics is that there are these really simple algorithms based on product formulas. There are these more sophisticated algorithms that, in some sense do better asymptotically. But I think, in practice, definitely for nearer term applications and maybe even for some, kind of longer term applications, it may actually really be better to use these kind of simpler algorithms, but using this kind of more sophisticated error analysis. So this is an area where, there's been a lot of work to sort of understand the best algorithms for this kind of abstract problem of Hamiltonian simulation, as I've described it here. There's also a lot of work on how concretely you can apply these methods to particular kinds of systems. For example, if you want to simulate chemistry, or if you want to simulate nuclear physics, or you want to simulate, some particular kind of system. There's many additional details to think about. For example, many of these systems involve, particles called fermions, and then there are questions about how do you map the fermions to the kind of qubits that you have in your quantum computer. So there's many other issues that I sort of don't have time to talk about. I think in general, this question of thinking about how you apply these kind of abstract algorithmic ideas to really concrete computational problems, where there's some possibility of getting out an interesting answer with a quantum computation that we couldn't find classically. I think there's a lot of important things to do there, but that's kind of maybe beyond the scope of what I'm gonna talk about today. Okay, so let me just very briefly mention a few other kind of directions in quantum algorithms, kind of relating to linear algebra, optimization, and machine learning. And these sections will be a little bit briefer. So first, linear algebra, right? So a kind of very basic problem that we see and kind of like all over, science and engineering is this problem of, solving linear systems of equations. So a simple setting here might be that we've got an n by n matrix A, we've got an n component vector B, and we want to find an n component vector X so that AX equals B. Of course, X is just, A is an invertible matrix, X is just A inverse acting on B. So that's the kind of linear systems problem. And, if we want to solve this problem, of course, if we want to write out the solution explicitly, then we're going to need to do an amount of work, linear in n, just to write out the solution. But something you can imagine trying to do on a quantum computer is to sort of change the model to one that's maybe in line with sort of the way we thought about the Hamiltonian simulation problem. Namely, that we've got some succinct representation of the matrix A with like a poly log n kind of amount of information. We've got the ability to efficiently, like in time poly log n, prepare a quantum state encoding the right-hand side of this system of equations, so like a normalized quantum state proportional to this vector B. And our goal is just to prepare a quantum state in the memory of our quantum computer, which is proportional to A inverse acting on this state ket B. And so, this is like a much more succinct representation of X, than writing out the vector explicitly, right? It's rather than sort of having to write down n things, this is a quantum state of only log n qubits. I mean, of course, from that state, you can't easily extract. I mean, and in fact, with only one copy, you can't even in principle extract what the explicit vector is. But it gives you some kind of summary that could be useful for some kinds of problems. In particular, it lets you measure, quantum observables on that state. And maybe that can tell you useful things. So what this paper of Harrow, Hassidim, and Lloyd showed is that actually you can solve this problem very efficiently on a quantum computer. You can prepare this quantum state in time like poly log n. And there's also some dependence on the condition number of this matrix, which tells you sort of how close to singular that matrix or how far from singular that matrix is. But in some cases, you could imagine preparing this state much, much faster than you could classically, find an explicit description of the solution of this system of linear equations. So, the details about how these algorithms work is, there's not really time to get into, but, basically what the algorithm does, it has to do with sort of like sort of eigenvalue estimation on this matrix using this notion of basically phase estimation on a Hamiltonian simulation that's related to the matrix A, and then with some process that involves post-selection, sort of only selecting certain kinds of good outcomes, and then paying for some overhead that comes from the fact that sometimes you may not get the outcome that you want, but you can take that into account in the complexity. You can basically effectively like replace an eigenvalue by its inverse, and that sort of effectively allows you to apply this matrix A inverse to the given vector B. And so since this original algorithm of Haro, Hessenheim, and Lloyd, there have been a bunch of improvements to the complexity of these algorithms, and in fact, there's even some algorithms that maybe work even better in practice that I haven't given the citations for here. So this is now something that's been pretty well studied. But now I guess the question is, what can this be useful for? And one kind of way to apply this algorithm has to do with trying to do a similar sort of thing for differential equations. So if you have a system of differential equations, you can imagine sort of using a kind of finite difference approximation to characterize the solution of this system of linear differential equations, by a system of linear equations. And then that's something that you can sort of approach using this quantum linear systems algorithm. And actually, by now, kind of quite a lot of algorithms have been written down that do this with kind of pretty good performance and handle a fairly general class of differential equations, including ones that have time-dependent coefficients, PDEs, even some cases where the equations are not linear, but we actually have nonlinear differential equations, although there's some significant limitations to those algorithms. So there's quite a lot of cases that have been studied in this setting. But now for both of these ideas of kind of quantum algorithms for linear equations or quantum algorithms for differential equations, I think the kind of thing which really is not super well understood is the extent to which these algorithms are actually useful for applications. So the kind of thing that makes it look like it could be promising is that linear equations and differential equations are like the bread and butter of all of science, basically. Like this is kind of how we characterize systems by linear equations and differential equations. So surely you could get some kind of quantum advantage for some concrete problem, at least you would hope, from these ideas. Pinning that down is a little bit slippery. So there have been some proposals for specific kinds of problems where maybe you could try to do this, having to do with actually classical physics, so like electromagnetic scattering problems, problems related to machine learning, problems related to numerical finance. A lot of kinds of settings that have been considered. I would say that none of these, however, have really led to a really compelling proposal for an application where there's good evidence that there's quantum speedup. So I think it's really not that well understood, and it's not clear how promising this is. So part of this comes from the fact that to apply this to some concrete problem, you have to think about the kind of input-output requirements. How do you come up with the specification of this matrix A and the vector B that allows you to prepare it? And what property do you measure of the state at the end? And all of the kind of overheads that come from having to do these kinds of things, need to be taken into account. And so, it's a little bit unclear, whether we can actually get good applications, kind of out of these ideas. Okay, so next, let me just say a little bit about optimization. So, there's been a lot of kind of discussion about the potential of quantum computers to give improvements for solving optimization problems. Certain kinds of improvements are kind of clear. So for example, Grover's algorithm can be leveraged to give some kind of quadratic advantage for minimization. And there are a bunch of other kinds of polynomial advantages for various kinds of optimization problems related to graphs, for example, finding short paths in graphs or finding minimum spanning trees or maximum flows. These are all kinds of things for which we can give polynomial quantum speedups. There are also some kind of polynomial speedups to algorithms for NP-hard problems, right? So we've got exponential time classical algorithms for those problems, and we can give still exponential time, but better exponential time quantum algorithms for those problems. Some of these algorithms have really introduced some interesting new tools, some of which are mentioned here. So there's been sort of, definitely work on this direction, but all the stuff that I'm mentioning here, this is like, kind of relatively modest improvements. This is about polynomial improvements to algorithms for optimization problems. that was in the setting of discrete optimization, and there's also a bunch that's been discovered in the setting of continuous optimization. For problems like linear programming and semi-definite programming, for kind of algorithms that either compute gradients or try to do gradient descent to minimize a convex function or more general functions. So there are a bunch of things that have been discovered. But again, I would say, now also in the setting of continuous optimization, the things that are sort of rigorous are by and large polynomial advantages. So the real question that I think, a lot of people would like to understand is there some hope for kind of getting exponential quantum speed up for optimization problems? And, one of the kind of frameworks, or maybe two of the frameworks that people have looked at related to each other to try to get they might hope for more significant advantages for optimization problems involve what's called adiabatic optimization and the quantum approximate optimization algorithm. So the kind of strategy for this idea of adiabatic optimization is to encode some optimization problem you would like to solve in terms of a diagonal Hamiltonian, to start in the ground state of some simple Hamiltonian, which is not diagonal, but whose ground state you can easily prepare, and to sort of slowly change the Hamiltonian to the one whose ground state would encode the solution of the problem you're trying to solve. And there's this thing called the adiabatic theorem, the quantum adiabatic theorem, that says that if you go slowly enough, you'll remain in the ground state the whole way, and this will allow you to solve the problem. But of course, the question is, how slowly do you have to go, right? This is maybe sort of analogous to like, this kind of setting where maybe you have a cup of water, and if you move it really fast, it's going to slosh all over. And if you move it slowly enough, it's going to sort of remain in its kind of, unexcited configuration. And you want to know how slowly you have to transport this thing, so that you don't like spill the cup. And so for this, adiabatic optimization problem, you can kind of characterize the complexity in terms of some spectral properties of the Hamiltonian, what's called the minimum spectral gap of this interpolating Hamiltonian. So that gives you some kind of characterization of the complexity, but this spectral quantity is kind of still, in general, very hard to estimate. So it doesn't really give an answer to the question. And maybe I'll skip this point. And so there's also this idea of the quantum approximate optimization algorithm, which can be seen as some kind of more discrete version of this adiabatic optimization, which has maybe related but distinct properties. So both of these approaches, kind of adiabatic optimization and the quantum approximate optimization algorithm, I guess they're hard to analyze in general. So you can think about them as heuristics that you could sort of try out to try to solve some optimization problems with a quantum computer. But it's not really understood whether there are problems for which they can give exponential advantage. And there aren't really compelling examples that have been found of good candidates for these algorithms to give significant quantum advantage. So I would say, from my perspective at least, the kind of utility of these methods is not so clear. Definitely, it would be a great thing to understand better. But going back to the point that I made at the kind of beginning of the presentation, I guess the real question is there some structure here that a quantum computer can take advantage of, that sort of really allows it to get the significant, speed up? And I would say there's not a good reason to think that there is such structure that these algorithms can take advantage of, or at least, that's whatever that structure is, if it exists, hasn't been clearly identified. So, whether optimization is a promising thing to think about with quantum computers, is I'm a little bit skeptical, but I think it's unclear. Okay, finally, I just want to mention machine learning. I have the least to say about this, but I want to at least mention it because it gets a lot of attention. So, there's this idea of trying to improve machine learning, which obviously is, affecting all of our lives and is kind of a very, impactful thing in the kind of context of classical computing. Can we bring this over to kind of the quantum computing world, and what can we say about quantum algorithms for machine learning? I think one of the challenges with trying to understand quantum algorithms for machine learning problems is that a lot of the success, the very impressive success of classical machine learning, is empirical. It's not like there's a lot of theorems about why machine learning is working so well. It just, seems like it does work really well. So, that's kind of a challenge for kind of quantum computing, where we don't have large scale devices where we can just try things out, and we're limited in what we can analyze with pencil and paper. So there have been some proposals for machine learning tasks using quantum algorithms. For example, this idea of recommendation systems from Karanitis and Prakash. And I would say for most of these things that have been proposed, actually, it has been shown that if you sort of give, you provide the sort of data structures that allow you to address the problem with those quantum algorithms, you can actually also exploit those data structures classically. And there's actually not, exponential quantum speedup in a kind of fair comparison between the classical and quantum algorithms. And I think this is the case for basically like most of the quantum machine learning proposals out there. There's not compelling evidence for exponential quantum speedup. So, identifying a sort of a case of a sort of a machine learning problem, a kind of natural machine learning problem that really had significant quantum speedup, provably had significant quantum speedup, this would be really nice. And I think in the absence of that, you have to ask yourself, or at least, at least I would be skeptical about, kind of the potential for quantum algorithms for machine learning. So, yeah, I think like for my taste, there's sort of too much attention or too much time, sort of spent on trying to find these quantum machine learning algorithms, relative to the kind of the promise or the kind of reasons to believe that there could be significant quantum speedups for these tasks. And sort of our inability to analyze them, and definitely our inability to just try them out given the kind of current state of quantum devices. One area that I think is kind of more promising in this direction is to think about, sort of computational learning theory. There's a nice survey of this area by Aaron Ashalom and DeWolf from a few years ago. And this is kind of a setting where you have kind of some well-defined access model where quantumly you can sort of like get coherent quantum access to concepts. And you can try to like think about, how efficiently you can learn from quantum examples. And here there's a lot of things that can actually be proven, and things are, I think sort of better understood than in the sort of like broader context of, what people sort of consider in this world of quantum machine learning. Okay, so I think I probably should wrap up. So let me just try to sort of conclude and give kind of an overview of sort of what I see of the potential for the future of the field. So I think it's kind of clear from our experience, over the past several decades of trying to think about what we can do with quantum computers, what kind of quantum algorithms might be possible, is that finding quantum algorithms is really hard. I mean, this is because quantum mechanics is not very intuitive. Of course, classical algorithms can do a lot, and we have to try to beat them to do something interesting with a quantum computer. And we have sort of limited techniques for quantum algorithms. We should certainly try to develop more. We've definitely come a long way. So we have new examples of exponential speedups that have been developed, new techniques. We have a much better understanding of an area called quantum query complexity that is a kind of really well behaved sort of setting in which we can think about the power of quantum computers. I guess maybe the last point I want to make is just that, if we really had large scale quantum computers, now I'm not talking about the kind of like, they're getting bigger, but they're still very noisy. I'm not talking about the kinds of devices that we had now, but if we really had, fault tolerant quantum computers with, large numbers of qubits, on which we could run, really large scale quantum algorithms, I would imagine that this could dramatically change our understanding of what it is that we can do with quantum computers, because we could just try things out. We could do the kinds of things that people do, empirically with classical computing. But before we get to that point, we're sort of stuck with what we're able to kind of do with pencil and paper, or maybe get some limited understanding of with kind of noisy devices. Okay, and then I'm just going to finish with this slide, which is a bunch of resources for sort of learning more about quantum algorithms. I have some lecture notes on this topic from a graduate course that I've given. There's a bunch of tutorials mentioned here from the QIP, conference over the years, one of which is a longer version of this talk that I gave, and a bunch of sort of surveys on particular topics in quantum algorithms that might be of interest.